All right, today we're going to start by talking more about net force. So we looked at this at the end of last semester as this idea that when multiple forces act on an object, they're either balanced or unbalanced. And when they're unbalanced, a net force exists. So we're going to look at that as far as what does that mean, but more importantly, how do we determine what that net force is? So I used a very basic tug of war example in our last set of notes, and we said the net force was this one extra person. So today we're just going to break down free body diagrams and to figure out how to find that net force. And then from there, in our next set of notes, we'll talk about how to apply Newton's second law to actually calculate the acceleration as a result of that. So we're going to start by kind of getting some big ideas. So the first idea is that many forces can act on an object at the same time. So by sitting in your chair, there's both the force of gravity and the normal force acting on you. But only net force will actually result in an acceleration. So right now, your net force is 0 because you're not accelerating. If you push your feet into the ground, you're applying a downward force, which would then cause you to stand up, in which case a net force exists. So this idea should hopefully remind you of one of Newton's laws. So one of the things we want to work on this quarter, or this unit especially, is sort of utilizing this left-hand space. So from time to time, I'm going to give you a question that I want you to think about. And you don't necessarily need to answer it now. Maybe it's something you come back to tomorrow when you're reviewing your notes. So what is this first statement? What does this statement here, which of Newton's laws are we using to define this concept? Is it the first, the second, or the third law? So if there are multiple forces acting on an object, the next thing we need to figure out is how exactly we go about finding this net force. In our definition of net force, we said it meant that there was one singular force in one particular direction that was larger than the rest. So in order to do that, we're going to look at forces and we're going to balance them out. But we're going to consider the perpendicular forces or the vertical forces acting on an object and balance those with each other. And then we'll do the same thing with the forces that are parallel to each other and balance those out. Whatever is then left over should indicate both the magnitude or the direction of the net force. So let's take a look at this in sort of a very generalized example. So I'm going to draw just a very basic object. And we know some forces that are acting on. So we always have, no matter what, the force of gravity. And since the object is on a surface, we're also going to have, sorry, my lines are terrible, some amount of normal force. If we pull on an object, we have some applied force. Go ahead and label these. And we're going to assume there was at least some amount of friction. So this is a fairly standard example. So though we said we wanted to talk about both the parallel and perpendicular forces. So let's start with perpendicular. So these are going to be at things that go 90 degrees from the horizontal. So in this case, we have force normal and force of gravity. So we would resolve those together. So perpendicular forces include things like gravity, normal force. If the object was falling through the sky, air would also, or air resistance. So in addition to perpendicular forces, we also have parallel forces. So in terms of parallel forces, we're going to look at those that are with the horizontal. So in this case, things that are often parallel are the applied force and usually the force of friction. And together, this gives us this idea of net force. So by adding, or the sum of, all the forces acting on an object is equal to the net force acting on the object. So this is kind of a big idea. Again, this symbol here is sigma, which just means the sum of. Because when we look at these forces, some of them are positive, some of them are negative, and we can add them all together. So we see, in this case, force normal is going up, so this would be positive. The force of gravity is going down, so it's going to be negative. The applied force is to the right, so it would be positive, and then friction would be negative. And if we had the actual numbers and we were to add them all up, we should end up with this net force. So we're going to look at a couple of examples to help kind of put this to work, and then I'm going to give you your practice problems, and that'll be it for our first look at net force. All right, so let's go ahead and take a look at a couple of examples. I'm going to go ahead and set these up as we go. So if you want to go ahead, I'll give a brief pause. These don't necessarily have to be super perfect. We're just going to look at 3 different examples. For the purpose of today's lesson, we're not going to talk much about the individual forces themselves. We're not really going to focus on gravity and normal and all of that. We're simply going to look numerically at some different interactions and decide first resolving parallel and perpendicular, and then finding out what's left over, and then giving a brief description about what that means for the object. So actually, before I give you the examples and while you are kind of sketching these down, I'm going to add some steps to solve in our left-hand column. All right, so steps to solve. Often we may need to draw and label a free body diagram that can help us organize the information that we're given in a word problem. We're then going to resolve, balance, solve, however you want to think about it, the perpendicular and then the parallel forces, and then we'll combine those together to find net force. And the last thing that we're going to do is to describe the resulting motion of the object. So what's happening based on the free body diagram now having some actual numbers to interpret that. So I'm going to kind of describe the example. I'm going to draw it as we go, and then we'll resolve the perpendicular. We'll then resolve parallel. We'll calculate the net force, and then we'll describe the motion. On the second one, I'm going to draw it all, and then I'm going to pause to give you some time to solve it, and then we'll go through the answer, and the same for the third. So I want you to try those on your own as we go. So for the first one, we're going to start with a downward force of gravity of 20 newtons. That's experiencing an upward normal force of 20 newtons. It's being pulled to the right with a force of 60 newtons, and it experiences a force of friction to the left of only about 20 newtons. So there's everything acting on our object. For the sake of consistency, I always start with perpendicular. Doesn't really matter. But in this case, my perpendicular forces are the 20 newtons up and the 20 newtons down. So in this case, I have positive 20 plus negative 20, which equals 0. So there is no net force up and down. Next, since there wasn't anything there, I move on to the parallel forces. So in this case, I'm resolving these two here. So for parallel forces, I have a positive 60 to the right plus negative 20 to the left, which leaves me with positive 40. I'm then going to kind of do a quick math problem here. 0 plus 40 is going to give me my net force. So F net equals positive 40 newtons. Again, force is a vector because we're talking about acceleration, so that positive is important. And then if I was going to describe this in very general terms, I might say that an object is moving to the right because my net force is to the right, experiencing some resistance. It's not significant, but it's also not frictionless. So it moves to the right with some resistance. So on the next one, I'm going to draw it, and then I'm going to give you some time where I'm not going to talk to let you kind of work through and solve, and then we'll kind of check together. So the first one we have is going to be a downward force of 50 newtons, an upward force of 50 newtons, a rightward force, rightward is a new word, of 15 newtons, and then a leftward force of 15 newtons. So again, in terms of process, we're going to first look at the perpendicular forces, then the parallel forces, which is going to land us at the net force, followed by your description. So go ahead and take a couple of seconds to think through this particular example. All right, so let's look, I'm not good with wait time, even in a video, perpendicularly. I have positive 50 plus negative 50. Again, zero net force here. In terms of parallel, I have positive 15 to the right, minus 15 to the left, and I again end up with 0. 0 plus 0 gives me 0 newtons of net force. So if there's no net force on the object, Newton's first law would tell us that that object must not be accelerating. But again, remember we said that could mean two different things. So what two things does it mean if the object is not accelerating?
Yes.
All right, hopefully, number one, you said it's at rest, so it's not moving. Or at rest. The other option is that it is moving, but at a constant velocity. All right, last guided example, and then you've got some practice ones to do on your worksheet. So on this third one, you'll notice that there is no surface, so we're talking about an object maybe in the air. So we're going to give it a downward force, gravity of 10 newtons, and an upward force of air resistance, that's about 5 newtons. Again, think about what is perpendicular, what is parallel, what is our net force, and then how would you describe what's going on? What explanation could you give? And certainly there are a couple of different options. All right, so in this one, perpendicularly, we have negative 10 newtons plus 5 newtons, 10 down, 5 up, is going to give us negative 5 newtons. In this case, there are no horizontal or no parallel forces, so we have 0. So our net force is negative 5 newtons. Remember that when we talk about vectors, the positive and the negative are indicators of direction. So in this case, in our falling object scenario, it makes sense that the object is moving downward. So the object is falling. With some air resistance. It's not in free fall. And actually, if we think about it, the air resistance is half of the force of gravity. So it's actually pretty significant in terms of basic air resistance there. So from here, you have kind of two options. We, with the PLC day for on-campus and virtual learners, you guys kind of being able to self-pace, there is sort of a part 2 to this lesson. So we've talked about net force, but we haven't spent any time really talking about where I got this 10 newtons of gravity, or how I know that normal force is 50 newtons. So in the next set of notes, which may or may not actually be done on the same day if you're in person, we're going to just look a little bit more closely at some of the individual forces that we've been talking about. So in this net force lecture, we talked in very general terms and I just gave you numbers. In the next piece, I'm going to kind of give a deeper definition of some of our forces so that you can actually calculate those numbers and then from there move into our net force calculations.